The Night Train, the Rail Wheel Metronome, a sleep story, third-person narrative. The complete story. The wheel clicked against the rail joint once more. No passengers counted the rhythm. The Northern Express had departed Union Station at 11:47 p.m., carrying its cargo of sleeping passengers across 847 miles of track toward the Dawn Terminal they would reach in 14 hours. Car 7, a sleeper coach built in 1987, rocked gently on its suspension system as steel wheels found their eternal rhythm against steel rails. The train moved through the darkness like a mechanical heartbeat, each wheel to rail contact marking time in the metronome of long-distance travel. Inside the coach, 64 passengers slept in their narrow berths, unaware of the complex symphony of systems that carried them safely through the night. But the train itself was far from sleeping. Every component, every sensor, every mechanical system maintained vigilant consciousness as the locomotive pulled its consist through landscapes that existed only as fleeting shadows beyond the windows. The wheel-to-rail interface created a percussion section that played continuously against the bass line of diesel engines 6 cars ahead. Steel wheels, each weighing 840 pounds, rolled along rails that had been welded into continuous ribbons of metal, interrupted only by expansion joints that provided the rhythmic clicking that became the train's signature sound. Click-clack, click-clack, click-clack. The metronome that measured progress in miles rather than minutes. But this rhythm had been playing continuously across thousands of miles, connecting cities through mechanical music that never paused, never varied its tempo, never lost its beat. The train's suspension system translated the vertical forces of track irregularities into gentle swaying motions that encouraged sleep in passengers who rarely noticed how carefully engineered their comfort was. Springs and shock absorbers between wheels and car bodies filtered out the harsh impacts of track joints and rail imperfections, transforming mechanical violence into soothing motion. Each car rode on 2 trucks, bogies that pivoted independently to follow curves while maintaining stability on straight track. These trucks were the train's feet, feeling every variation in the roadbed, every change in grade, every curve in the alignment. The wheels themselves were marvels of metallurgical engineering, forged steel discs that had been precisely balanced to eliminate vibrations that would disturb passenger comfort. Each wheel was matched to its axle mate with tolerances measured in thousandths of inches, ensuring that weight distribution remained perfect even as the wheels wore gradually against the rails over hundreds of thousands of miles of service. Now imagine lying in your berth, feeling the gentle sway of the car as it follows curves laid out by engineers who understood that trains, like rivers, must flow naturally through the landscape. The rail system beneath the train represented one of humanity's greatest infrastructure achievements. Parallel lines of steel stretching across continents, maintained to tolerances that ensured smooth passage for vehicles traveling at highway speeds while carrying loads that would crush any road surface. These rails were not merely metal strips, but precision-engineered pathways that guided the train with mechanical certainty toward distant destinations. Track geometry systems continuously monitored the alignment and elevation of these steel highways, detecting variations that could affect ride quality or safety before human passengers could perceive them. Electronic sensors measured rail position to fractions of inches, ensuring that curves remained smooth,
grades stayed consistent, and the mechanical music of wheel against rail maintained its hypnotic rhythm. The locomotive's diesel-electric propulsion system provided the steady bass note beneath the percussion of wheels. 6 diesel engines, each producing over 4,000 horsepower, turned generators that fed electricity to traction motors mounted on each driving axle. This system eliminated the need for mechanical transmission, providing smooth acceleration and the ability to maintain constant speed regardless of grade or load. Listen to the harmony. Diesel engines providing power, electric motors translating that power to motion, wheels maintaining rhythm, rails guiding direction, all coordinated in mechanical symphony. Inside the sleeper cars, HVAC systems worked quietly to maintain perfect atmospheric conditions for rest. Air circulation systems moved fresh atmosphere through each car while filtering out the dust and pollutants of industrial landscapes the train passed through during its overnight journey. These systems understood that sleeping passengers required different atmospheric conditions than daytime travelers: cooler temperatures, lower humidity, minimal air movement. Thermostats in each car adjusted heat output based on outside temperature and passenger load. The train's water systems supplied restrooms, hand-washing facilities, and drinking fountains throughout the passenger cars. Fresh water tanks held hundreds of gallons, while wastewater systems managed the disposal of used water according to environmental regulations. These systems operated independently of external water supplies, making the train self-sufficient for the duration of its overnight journey. The train carries its own mobile city, complete with utilities, services, and amenities that function independently while traveling at speed through landscapes that provide none of these services of their own. Food service systems in the dining car maintained refrigeration for meals that would be served hours later when passengers awakened to find themselves in different time zones from where they had fallen asleep. Kitchen equipment remained ready to prepare breakfast for travelers who would greet the morning hundreds of miles from where they had said goodnight. The train carries its own mobile city, complete with utilities, services, and amenities that function independently while traveling at speed through landscapes that provide none of these services of their own. Emergency systems throughout the train prepared for situations that railway engineers hoped would never occur. Emergency braking systems could stop the train in minimum distance if dangerous conditions developed ahead. Emergency communication systems could summon assistance to any location along the route. Emergency lighting systems would activate if primary electrical power failed, ensuring that passengers could evacuate safely even in complete darkness. The locomotive's event recorder, the railway's equivalent of an aircraft's black box, continuously documented the train's speed, braking applications, horn signals, and engineer actions. This system created a permanent record of the train's operation that could be analyzed if any incidents occurred. But more importantly, it provided data about normal operations that helped improve railway safety and efficiency. Track maintenance systems along the route monitored the condition of rails, cross ties, and ballast that supported the train's passage. Automated track inspection vehicles had recently traveled this route, measuring rail wear, detecting broken spikes, and identifying any defects that might affect train operations. The track structure was maintained to standards that ensured safe passage for trains traveling at authorized speeds. The railway infrastructure represents a continuous maintenance challenge. Thousands of miles of track, signals, and equipment that must function perfectly to ensure safe passage for trains carrying hundreds of passengers through the night toward destinations they will reach in the promise of morning light. car positioning systems tracked the exact location and orientation of each car as the train navigated curves, climbs, and descents along the route. These systems ensured that cars remained properly aligned and that coupling forces stayed within safe limits even as the train encountered varying track geometry and elevation. These systems compensated for the different ways cars responded to curves and grades based on their weight and load distribution. Ventilation systems in the sleeper cars exchanged interior air with filtered outside air, maintaining air quality for passengers who would sleep for hours in enclosed spaces. These systems operated quietly to avoid disturbing sleep, while ensuring that carbon dioxide levels remained healthy and that any odors or contaminants were quickly removed from passenger areas. The train lighting systems automatically adjusted illumination levels throughout the cars based on time of day and passenger activity levels.
Corridor lighting dimmed to levels that provided safety illumination without disturbing sleeping passengers. Reading lights remained available, but were designed to provide localized illumination that would not affect other passengers in the same car. Even lighting becomes part of the train's consideration for passenger comfort, adjusting automatically to support natural sleep rhythms while maintaining safety and convenience for passengers who might need to move through the train during night hours. Sound dampening systems throughout the passenger cars reduced the transmission of mechanical noise from wheels, suspension, and propulsion systems. Special materials in car construction absorbed vibrations and sound waves that could disturb passenger sleep. Windows were designed not just for viewing, but for acoustic isolation, keeping external noise outside while maintaining comfortable sound levels inside. The train's consist included cars designed for different passenger needs: sleeping cars with individual berths, coach cars with reclining seats, dining cars for meal service, and baggage cars for checked luggage. Each car type required different mechanical systems and different maintenance schedules, but all were coordinated to operate as components of a single transportation system. Climate control systems adjusted not just temperature, but humidity levels throughout the train, maintaining atmospheric conditions that promoted comfortable sleep. These systems drew outside air through filtration systems that removed pollutants and allergens, ensuring that passengers breathed clean air, regardless of the industrial or agricultural regions the train passed through during night hours. The train creates its own atmosphere, independent of external environmental conditions, maintaining perfect air quality and comfort for passengers who sleep while traveling through regions where air quality might be compromised by industrial activity or agricultural operations. The locomotive's dynamic braking system converted the train's kinetic energy back into electricity when descending grades, reducing wear on brake shoes while providing precise speed control. This regenerative braking system allowed the engineer to maintain constant speed on long descents without overheating conventional brakes, ensuring smooth travel for sleeping passengers even through mountainous terrain. Suspension systems in each car adjusted their characteristics based on passenger load and track conditions, providing optimal ride quality regardless of how many passengers occupied each car or what type of freight trains had recently used the same tracks. These adaptive systems ensured consistent comfort levels throughout the journey, even as conditions changed. The train's communication systems included both voice and data networks that connected all cars and provided links to external railway operations centers. These systems carried not just operational communications, but also maintenance data from onboard systems that monitored equipment condition and performance. Diagnostic information flowed continuously from car systems to central computers that tracked equipment health.
Data flows through the train like an electronic blood, carrying information about system health, operational status, and performance metrics that ensure all equipment functions optimally throughout the journey while providing early warning of any potential problems. Lighting systems along the railway right-of-way illuminated the train's passage through urban areas while remaining dark through rural regions where light pollution would disturb natural environments. These systems coordinated with the train's approach, activating only when needed to provide visibility for railway workers or warning systems for road crossings. The train's horn system provided audible warnings according to standardized signals that communicated the train's approach, direction of travel, and operational status to anyone who might be near the tracks. Horn sequences varied based on track types, track conditions, and operational requirements, creating a vocabulary of sound that experienced railway workers could interpret from miles away. Mechanical systems throughout the train performed self-diagnostics continuously, monitoring their own performance and reporting any variations from normal operating parameters to central diagnostic systems. These monitoring systems could detect developing problems before they affected service, allowing for maintenance interventions that prevented service disruptions. The train monitors its own health with the same vigilance that medical professionals monitor patient vital signs, detecting changes in system performance before problems develop into failures that could affect passenger service or safety. The locomotive's fuel systems managed diesel consumption across multiple engines, optimizing fuel usage for the varying power demands of different terrain and operating conditions. Fuel injection systems adjusted delivery rates thousands of times per minute, ensuring optimal combustion efficiency while minimizing emissions from the diesel engines that provided power for the entire train. Car trucks, the wheeled assemblies beneath each car, contained sophisticated bearing systems that allowed wheels to rotate freely while supporting enormous loads. These bearings were designed to operate for hundreds of thousands of miles with minimal maintenance, using advanced lubricants and sealing systems that protected critical components from contamination. The train's electrical distribution systems routed power from locomotive generators to hundreds of different systems throughout the train consist. Electrical cables ran the entire length of the train, carrying power for lighting, HVAC, communication, and safety systems in each car. These systems included backup power capabilities that ensured essential systems remained operational even if primary power generation failed. Electricity flows through the train like the nervous system of a living organism, powering systems that maintain life support, communication, and coordination throughout the mechanical body that carries passengers safely through the night and into the house of the midnight. Track geometry ahead of the train had been precisely surveyed and constructed to provide smooth transitions between straight track and curves, level track and grades, single track and multiple track sections. Railway engineers had designed these transitions to minimize the forces that passengers would feel, ensuring that changes in direction or elevation occurred so gradually that sleeping passengers would not be awakened by sudden motions. The train's weight distribution systems ensured that loads remained balanced across all axles and wheels, preventing excessive wear on any individual component while maintaining optimal traction and braking performance. Load sensors monitored weight distribution continuously, compensating for passengers moving within cars or changes in fuel and water supplies as the journey progressed. Safety systems monitored the integrity of critical components throughout the train, from wheel bearings to brake systems to electrical connections between cars. Hotbox detectors along the route used infrared sensors to detect overheating bearings or brake systems, automatically alerting the engineer if any dangerous temperature conditions developed anywhere in the train consist. Safety sensors create an invisible network of protection around the train, monitoring everything from bearing temperatures to electrical system performance, ensuring that potential problems are detected and addressed before they can compromise passenger safety. The locomotive's control systems integrated input from hundreds of sensors and switches throughout the train, coordinating the operation of propulsion, braking, communication, and safety systems throughout the train. These control systems processed information continuously, making adjustments to train operation based on track conditions, signal requirements, and performance optimization algorithms. Car coupling systems transmitted not just mechanical forces, but also electrical connections and pneumatic brake lines between cars, creating integrated systems that functioned as single units despite being physically separate vehicles. These connections allowed the locomotive engineer to control braking and other systems throughout the entire length of the train from the locomotive cab. The train's schedule system coordinated its progress with other train movements, station operations, and maintenance activities throughout the railway network. Dispatchers monitored the train's progress and communicated any schedule changes or operational requirements to the onboard crew, ensuring coordination with connecting services and facility availability at the destination terminal. The train operates within a complex network of coordinated activities, its movement synchronized with other trains, maintenance operations, and station services across thousands of miles of railway infrastructure that must work together to provide reliable passenger service. Environmental control systems throughout the train maintained not just temperature and air quality, but also noise levels, vibration damping, and lighting that supported passenger comfort
and natural sleep rhythms. These systems understood that night travel required different environmental conditions than daytime service, automatically adjusting their operation based on time of day and passenger activity levels. The train's navigation systems used GPS technology combined with track-based positioning to provide precise location information for operational control and passenger information systems. These systems could track the train's position to within feet while calculating arrival times at upcoming stations based on current speed and known track geometry ahead. Emergency evacuation systems throughout the train prepared for situations where passengers might need to exit the train between stations. Emergency windows, exits, and evacuation slides could be deployed quickly if dangerous conditions required passenger evacuation in remote locations. These systems included communication equipment that could summon emergency response teams to any location along the route of the thousands of miles that the train traverses during its overnight journey. The locomotive's data recording systems captured not just operational information, but also track geometry, signal performance, and environmental conditions encountered during the journey. This information contributed to databases that helped railway engineers understand system performance, optimize operations, and plan maintenance activities across the entire railway network. The passenger information systems throughout the train could provide announcements about arrival times, connecting services, and station information. But during night hours, these systems operated quietly to avoid disturbing sleeping passengers. Visual displays remained active for passengers who might be awake, but audio announcements were minimized to maintain the peaceful environment needed for rest. The train's mechanical systems had achieved a level of integration where individual components worked together with precision that approached biological coordination. Wheels, suspension, propulsion, braking, and control systems functioned as organs in a mechanical organism that carried passengers safely and comfortably across landscapes while they slept.
The train has become a mechanical organism, its various systems functioning with biological coordination to maintain the health and safety of passengers who rest within its protective envelope as it travels through the night toward destinations they will reach refreshed and ready for new adventures. All these systems continued their vigilant operation through the hours of darkness, maintaining their electronic and mechanical consciousness while passengers slept peacefully in their berths, unaware of the complex symphony of engineering that carried them safely toward morning. The train's systems felt no fatigue from their continuous operation, experienced no boredom during the long hours of night travel, knew only the satisfaction of perfect mechanical performance. The rhythm of wheels against rails continued its hypnotic beat, a metronome that measured not just distance, but time itself, marking the passage of night hours with mechanical precision. Each wheel-rail contact contributed to a percussion symphony that had been playing continuously since the first trains began rolling on the first railways, a mechanical music that connected all railway travel across history. The rail wheel metronome plays a rhythm that connects your journey to every railway journey that has ever been taken, every passenger who has ever slept while being carried safely through the night by steel wheels on steel rails. And you, listening to this mechanical lullaby, can rest in the knowledge that railway engineering has created one of humanity's most reliable and safe forms of transportation. The systems that surround you represent centuries of engineering evolution, each component refined through millions of miles of service to achieve reliability that exceeds most human activities. The train's gentle mechanical meditation continues as consciousness fades, the steady rhythm of wheels guiding you into peaceful sleep. In the morning, you will awaken in a new city, refreshed and ready for new adventures, carried safely through the night by mechanical systems that never sleep, never tire, never cease their vigilant protection of human cargo they carry through the darkness toward the light of dawn. Sweet dreams, cradled in the mechanical embrace of steel and engineering, carried safely through the night by the eternal rhythm of the rail wheel metronome that measures your journey in mechanical time toward destinations that wait in the promise of morning.